Okay, so today we are going to talk about the Lagrangian with constraints. Okay, so there are many systems like this one. This rolling down an inclined plane without slipping. Rolling without slipping is a constraint. Um, in this example, the constraint condition can be explicitly written out, and we can easily incorporate the constraint into the Lagrangian and eliminate some of their variables, right? However, in other cases, the constraints may not be incorporated into the Lagrangian so easily. So we would like to we need some other alternatives to incorporate the constraints. One way to do it is using the undetermined Lagrange multipliers. I believe that all of you have learned about the Lagrange multipliers when you are asked to find the extrema of a function or of a certain quantity, right? And the idea is exactly the same. So let's start now. Given the Lagrangian of a system with constraints, expressible in differential forms like this. Okay, say for example, rolling without slipping, y equal to r theta. So we will have the constraint is f equal to y minus r theta equal to 0. So we differentiate f with respect to y and also differentiate f with respect to theta. Okay, and obtain this differential form for the constraint equation. Now, given this constraint differential form, the Euler-Lagrange equations can be modified to include these constraints conditions to give a modified version of the Euler-Lagrange equations, as shown in equation 12, in equation 2. Okay, so without constraints, the third term will disappear. With constraints, it show up here as the third term, and lambda k are the undetermined Lagrange multipliers for all the constraints, all different constraints. If we have only one constraint, so of course there's only one parameter. And these multipliers are closely related to the generalized forces of constraints. Say, for example, rolling, in the example of rolling without slipping down in inclined plane, the generalized forces are the torque and also the force and also the reaction, normal reaction, right? And all these. Okay, I'm not going to go through all the details about deriving the Euler-Lagrange equation motion. Okay, you can try it, do it by yourself, and discuss with the TA. Now, the usefulness of the method of undetermined multipliers is twofold. First of all, the Lagrange multipliers are closely related to the forces of constraint that are often needed. Say, for example, the torque and also the downward force for the example of a ring rolling down an inclined plane without slipping. When a proper set of generalized coordinates is not desired or too difficult to obtain, the method may be used to increase the number of generalized coordinates by including constraint relations between the coordinates. It means sometimes the generalized coordinates are related related in a very complicated way, complicated form. So it's hard to eliminate some dependent variables. So the Lagrange multipliers method may help us to bypass this difficulty. Okay, so let's try to understand. I think to understand the method of all undetermined multipliers in Lagrangian formulation is through the examples. Okay, the first example. So we have a disk rolling down an inclined plane without slipping, as shown in the diagram. So we are asked to find the equation of motion, the force of constraint, and the angular acceleration, right? Now we have encountered this before within the context of Newtonian mechanics, right? We are not going to repeat that here. Sorry about. So to begin with, we need to find the kinetic energy and potential energy, right? Potential energy comes from the gravitational force. Okay, kinetic energy, the translation kinetic energy, 1/2 my dot square. The rotational kinetic energy, 1/2 I theta dot square, right? Y is in this direction. This is the rotation. So translational kinetic energy, rotational kinetic energy, right? I is equal to the moment of inertia is equal to 1/2 mr squared for a disk, okay, about our central axis. So we obtain the kinetic energy easily. How about potential energy? It is equal to mg L minus y sine alpha. So we set the reference level at here. Okay, we set the reference level here. L is the length of the inclined plane, and this is assumed to have zero potential at the bottom of the plane. Okay, combining T and U together, T minus U, we have this, equation 6. It is written in equation 6. So what's the next step? Since we have rolling without slipping, so we have a constraint condition. And here we see that there are two generalized coordinates. One is y, the other one is theta, okay? Two independent variables. Now we have one constraint condition. In other words, one of the variable is not independent. In fact, there is only one independent variable in this problem. So this is the constraint equation. Y minus r theta is equal to 0. Okay, so y is related to theta. Hence, the system has only 1 degree of freedom. So we may choose either y or theta as the proper coordinate and use the constraint equations to eliminate the other. Here, what we try to eliminate the theta. All right. So theta dot is equal to y dot divided by r. So we substitute this into the Lagrangian here. So the theta dot is replaced by y dot over r. So this is our simplified Lagrangian as shown in equation 8. Now you can see that no dependence of theta anymore, theta or theta dot anymore. Now the corresponding Euler-Lagrange equation motion is given by this. How do we get this? We differentiate L with respect to y dot and then differentiate the resultant quantity with respect to t. So we get this. And we differentiate the L with respect to y. Okay, and we get this. So this is the Euler-Lagrange equation. After simplification, we find that y dot is equal to this. Okay, it's a constant. Once we find the once we have this equation, we can find y. Okay, y dot and y. After obtaining y dot and y, we can find theta dot and theta. Okay, so that's our the standard. That is the uh, conventional way to do it. However, alternatively, we may continue to consider both y and theta as independent generalized coordinates and apply the method of undetermined multipliers. How? So we add this extra term. Lambda is the undetermined multiplier. Since we only have one variable, so we have round f round y. Sorry, since we have two variables, and the first equation is related to y, so we have a round f round y. The second equation is associated with theta, so we have round f round theta. Okay, so the first the Euler-Lagrange equation motion in y gives you this. The Euler-Lagrange equation in theta gives you this. All right. And from the constraint equation, we realize that y is equal to r theta. So differentiating this, we have theta dot double dot equal to y double dot divided by r. All right. Combining equation 13 and equation 11, we obtain the Lagrange multiplier, which is equal to minus 1/2 my double dot. And then substituting this expression into equation 10 here. We know lambda, we substitute it back here. Then we obtain an equation involving y double dot. Okay. Once the y double dot is known, we can find we can determine lambda according to equation 14. Right? And also, since y double dot is known, so theta double dot is known as well by dividing y double dot by r. Okay, so we have an equation in y double dot, an equation in theta double dot, and an expression for the Lagrange multiplier lambda. All right. As a result, we have three equations for the quantities y double dot, theta double dot, and lambda that can be integrated readily. Now, the generalized forces of constraint are given here. The generalized force of constraint associated with y is given by lambda round f round y. Okay, round f round y gives you 1. So qy is equal to lambda. And the lambda is given here. It's equation 16. Q theta is the generalized force associated with theta, which is equal to lambda times round f round theta. After differentiation, we have minus lambda r. Okay, and this is equal to minus mgr sine alpha divided by 3. Now, what is qy? That is a force. The force pulling the disk, and q theta is the torque rotating the disk. All right. So the method of Lagrange multiplier gives you additional information about the constraint forces, and also and also the angular acceleration. Right. Second example, a particle of mass m moving on the surface of a fixed smooth hemisphere. All right. So it's moving on this hemisphere, on the surface of this hemisphere. Find the force of constraint. Obviously, that is the normal reaction. And determine the angle at which the particle leaves the hemisphere. Right. Again, this problem has been dealt with using Newtonian mechanics in previous courses. So how do we tackle it? We can set up the Lagrangian function in terms of the kinetic energy and potential energy, and then obtain and then write down the constraint equation. Making use of the constraint equation, we can eliminate the unknown, one variable, either theta or r, and then we have a lower degree, a lower number of degree of freedoms. Then we can write down the Euler-Lagrange equation motion associated with the remaining variable. Right. The second approach is to make use of the undetermined Lagrange multiplier. Okay, we will choose the second approach. Kinetic energy, radial kinetic energy. The first term gives you the radial kinetic energy. The second term gives you the angular or tangential rotational energy. Okay, tangential kinetic energy or rotational kinetic energy. The first term, radial translational kinetic energy. Potential energy is equal to mgr cosine theta. Right? mgr cosine theta. Okay, so you can see that when theta equal to pi over 2, the energy is equal to 0. And it is at the top of the hemisphere, it is equal to mg cosine 0. And has the largest potential energy. Lagrangian, L equal to T minus U, the kinetic energy minus the potential energy. Right? It's given in equation 22. Keep in mind that the potential energy is 0 at the bottom of the hemisphere. Now we have a constraint equation, R minus A equal to 0. A is the radius of the hemisphere. Now we have this constraint equation, then we make use of, we apply the method of undetermined Lagrange multipliers, okay? So we obtain two Euler-Lagrange equation motion. The first one in R, the second one in theta. And these are the third term in equation 1 and equation 2 corresponds to the constraint they come from the constraint equation, right? So the the Euler-Lagrange equation motion in R given in equation 24. The Euler-Lagrange equation in theta is given in equation 25. Okay. Now the constraint equation tells us that R equal to A. So R dot equal to 0, R double dot is equal to 0. So equation 24 and 25 become mr theta dot double dot theta dot square minus mg cosine theta plus lambda, because r double dot equals 0. The second order Lagrange equation motion is given by, can be simplified to mga sine theta, because r equal to theta, r equal to a, and minus ma theta dot a square theta double dot, and we immediately find a nice equation for theta double dot. Theta double dot is equal to g over a times sine theta. Now, it is not difficult to show that by direct integration, we can find the theta dot square, okay? Theta dot square by chain rule. So d theta dot dt is equal to d theta dot d theta times theta dot, all right? A standard trick. So we can obtain a solution like this for theta dot square. Once we obtain this theta dot square, we can substitute it into equation 28. Then we can obtain lambda readily, okay? And we know that the generalized force of constraint in our direction is given by lambda round f round r, and round f round r is equal to 1 given here, okay? So the generalized force of constraint in our direction is equal to lambda, and and lambda is equal to mg times 3 cosine theta minus 2, as shown here. Because we know the theta dot square, so we substitute here, and we can obtain the number ready. All right. Now, the particle falls off the hemisphere at angle theta dot when the force of constraint vanishes. In other words, when lambda equal to 0, right? So lambda is given by this. We set it equal to 0. So theta dot is equal to the arc cosine 3 over 2, 2 over 2/3. Since r equal to a, r dot equal to 0. So the Lagrangian can now be reduced to this. Okay, we just eliminate all the r. If we incorporate this constraint, obviously the system has only 1 degree of freedom. The Euler equation is given like this. So this is another approach. We incorporate this constraint into the Lagrangian directly, and there's only one variable, independent variable, and we have only one Euler-Lagrange equation motion, and that is associated with theta. So we have our Euler-Lagrange equation motion in theta, and performing the necessary differentiations, the Euler-Lagrange equation motion is given by this. Okay, now these two examples are very simple. We have seen these two examples before. Actually, we are familiar with these two examples. Right? However, do you have any questions about the procedures of incorporating the constraint via the method of Lagrange multipliers? Any questions so far? Now, can any one of can one of Can any one of you to tell me how to solve this? And sorry, let me how do I the constraint given the operation? Why does the force of constraints keep that form? Okay, the constraints condition is given in the problem. So like this, rolling without slipping. So we know that y equal r theta, and it is customary to write down f, define the function f equal to r y minus r theta equal to 0. All right. Same for the second example. We know that the r will never change. R must be equal to a. All right. So the constraint function f will be equal to r minus a. Okay, f equal to r minus a equal to 0. Okay. Now, why do we define? How can we define this as generalized forces of constraints? Now, if you go through the derivations here, as asked in exercise 1, and compare the terms, all right? Compare the terms. We know that this is the term responsible to force, okay? Because this is the mass time for simple cases. This is the mass time the acceleration. Okay, for example, in a one-dimensional problem, simple problem, all right? And this is basically the force, because usually in simple cases this term involves the potential energy, right? So gradient differentiating the potential energy with respect to the coordinate will give you the force. So this is related to the constraint. So this is the force of constraints, right? Now here's my, I would like to ask you questions now. Let us go back to Newtonian mechanics. Can someone, okay, consider this as a SDOT classes. Can someone tell us how to do it through using Newtonian mechanics method? All right, can anyone volunteer to teach us how to solve example 1 and example 2 using the Newtonian mechanics? So kind of a review. Okay, let me ask someone to do it. How about Kenneth Wong? Can you try it? Kenneth Wong. Can you try it? Newtonian mechanics.
Can you hear me?
Yes.
For question 1, I think we could use talk to solve the problem.
How?
So we write the the gravitational force component along the surface, along the plane. Then we can apply torque equals to I alpha. Then I think we can get the force of constraint too.
Now, using Newtonian mechanics, how you just pretend that we are your students. We do not know anything. Okay, this is a new example. We just learned Newtonian mechanics. Can you tell us step by step how to tackle this problem? What is the first step? Second step? Kenneth?
I think first step is to draw a Fibonacci diagram and decompose the force
Okay,
and say along the plane and normal to the plane.
okay,
Then we could use net force equals to ma along the plane,
right.
the Newton's second law, and we can also use the torque version of the second law to do the similar things.
You mean the torque for the rotation?
Yeah, yes.
Okay. What else?
And
So we have
then
equations.
then we can solve the differential equation to obtain the equation of the motion.
Right. Now, we have one equation for my double dot equal to the force along the plane, and then I theta double dot, am I right, equal to the torque, and what else? The constraint equation, am I right? So we have three equations. Am I correct? Okay, so we have three equations. So then we make use of the constraint equation. We can eliminate one of the equation of motion. Say, for example, the rotation, the angular motion. Then we can solve the remainder one. All right. Okay. Okay, the second example. This is a little bit tricky. Second example. How about 張國正？張國晴啊？張國清。Can you try it? Hello?
Hello, can you hear me?
Can you hear me?
Yeah, I can hear you.
Okay.
So
using Newtonian mechanics.
So for the rotational part, maybe this just similar to example one is use the the friction times the wait. Oh,
There's no friction.
Oh, there's no friction. Also, there is only translation. So just use the take the component of mg respect to. Oh, let me see. Because well, in is mg sine theta equals to oh well sorry, maybe I don't really know how to do it.
You forgot how to do it now.
It seems need to use differential equation, but I don't have paper and pen, so I can't do it now.
Okay. Let me ask another one. Trần Nhân Mong. Can you try it?
So let me think about it. So basically, if it moves along the smooth hemisphere and assume it is bounded to the hemisphere, then at a certain time, the centripetal direction, there is an acceleration, and that acceleration should be given by v squared over r.
Okay.
And then so we require the radial direction of the force to be equal to that thing, and also, and for the tangential part, probably will become the angular speed.
Okay.
I mean angular acceleration.
Yes.
And then probably there would be two equations, and somehow it would be done.
All right. So you write down the force diagram, and then the radial motion, and then the tangential motion, right? And you of course you put in the constraint A equal to R equal to A. And how do we determine the angle at which the particle leaves the hemisphere? The normal reaction will become zero, right? The normal reaction will become zero. So after solving the equations, you determine the normal reaction. And if the normal reaction vanishes, then the particle leaves the hemisphere. Okay, so I hope that it give you some some idea how to use the Newtonian mechanics to solve this problem. Okay, you have to be a bit more careful when you use Newtonian mechanics. You have to identify the correct forces, identify the correct motions. Okay, and then put in the appropriate constraints. However, if you use Euler the Lagrangian formulation, is basically very routine. What you need to do is to follow the a series of steps, a set of steps, one by one. Say, first of all, write down the coordinates of the particle, as in Greek example 1 and example 2, and then determine the kinetic energy, potential energy. Making use of the kinetic energy and potential energy, we can find the Lagrangian function, and then we put in the constraint conditions. Then we can apply the standard method to derive the Euler-Lagrange equation motion. Right? Using the method of undetermined multipliers, we can also determine the constraint forces and also the Lagrange multipliers automatically. So everything becomes very systematic. We just follows a set of systematic steps, and we can get the answer. All right. So this is the powerful, the most powerful aspect of the Lagrangian formulation or analytic mechanics. Okay. All right. Let us move on. So the third example, Edwards machine. So we have a pulley here. There is a string connecting M1 and M2, right? So we can write down the Lagrangian. The Lagrangian contains two parts, kinetic energy and potential energy. So the kinetic energy for M1 is given by 1/2 M1 L1 dot square. The potential energy for the M2 is 1/2 M2 L2 dot square, right? The potential energy is equal to minus M1 GL1 and minus M2 GL2, all right? The potential energy at this level is equal to 0. The constraint equation, L1 plus L2 equal to L, okay? Because the L is the string of the total the total length of the string, neglecting this half circular arc. Okay, so this is the constraint condition. Then the corresponding Euler-Lagrange equation motion is given by this. 1 m1 L1 double dot minus m1g minus lambda equal to 0. So we can move the lambda to the right hand side. And we can automatically identify the first equation as the Q1 and the second equation as the Q2, because rank F rank L1 equal to rank F rank L2 equal to 1. So the Q1 and Q2 are the generalized forces, constraint forces. According to the three equations in equation 36, 37, and 38, we know that 36 implies L1 equal to minus L2 double dot, L1 double dot equal to minus L2 double dot. Subtracting equation 38 from equation 37, subtracting 38 from equation 37, we get this. So we obtain L1 double dot to be a constant given by this. Now substituting equation 40 back into equation 37, we can obtain the Q1 and Q2 equal to lambda equal to this. Right. So you can see that through a series of systematic steps, we can find the solution of the equation motion. We can find the Lagrange multipliers. We can also obtain the generalized constraint forces one by one. Okay, so very powerful method. So can I ask what Q1 and Q2 correspond to? What are these generalized constraint forces? Can anyone tell me? The tension, right? The tension of the string. Now, this is an exercise for you. We have one cylinder of mass m and radius r2 rolling without slipping on another cylinder of radius r1. Okay. Find the equations of motion and the forces of constraint. So I hope that you will try to work it out by yourself first. After that, we will discuss it. All right. Okay. So far, any questions about these materials? In order to have a better understanding of Lagrangian with constraints, I think you have to explore more examples, work on more examples or exercises. Then you can finally appreciate its usefulness. Right? Any questions? No more? Okay. Now, I think that I will stop the lecture class now, and I will stay online till 1 o'clock. If you have any questions about the course materials, just chat with me and chat with me. Okay. If you If you don't have any questions, then you can leave. If you have questions, just stay here and ask me. All right. Okay, the lecture class